we tested over 160,000 modules in 25. And we had the highest defect rate we've ever seen, which was 3.36%. May not sound like much, but really when you're looking at other industries having a 3.36% defect rate is pretty high.
Some of the breakage has been on the rear side glass.
I would say almost all.
Really? Okay.
Almost all happening. But if it is so fragile that, a little pebble or stone can actually, completely destroy the module at the end of the day, you have to ask yourself if the glass is really fit for purpose. And that's where we are right now.
It's a perennial question in an industry where things move fast and there's always downward pressure on costs. How do we build and design PV projects to stand the test of time? Well, that was under discussion this week in Barcelona at the Solar Quality Summit. And this is the Smartery podcast. I'm your host, Jonathan Gifford. So how can solar quality be maintained? Well, there's no one silver bullet or one solution to this challenge. And it really is a multifaceted one. One of those angles or developments that was under discussion here in Barcelona this week was artificial intelligence and machine learning, and how things like automation and robotics can be used to ensure quality at PV projects right across the supply chain. We're going to discuss this topic along with the importance of materials, things like glass and polymers, on this episode of the podcast today, and of course, PV cell and module degradation, causes, and different modes of failure. I've got two guests on the podcast today. Kiwa Berlin is a researcher, sustainable polymer solutions with the Polymer Competence Center Leoben, the PCCL, and Steven Jureb, who is the executive director of Kiwa PI Berlin. But before that, just a quick word from us here at the Smartery Pod. If you're listening or watching the pod for the first time, please do subscribe, follow, or leave a rating and review. It really does help us to get the word out. At the Smartery Pod, we're really trying to get correct, accurate, and up-to-date information about the energy transition. So it really helps to get as big an audience as possible. And of course, you can get in touch with us anytime at podcast@thesmartery.com. In early February, Kiwa PI Berlin released its Module Manufacturing Report 2025, which for anyone who's interested in quality and durability, it's pretty much a must read. Here at the Solar Quality Summit, Steven Jureb, the executive director at PI Berlin, Kiwa PI Berlin, took us through some of the findings of the recent report and now joins us on the Smartery podcast. Hi, Steven.
Jonathan, thanks for having me.
Great pleasure. Now let's dig into the report, dig into what some of the findings that you made were. Just on a high level, where are we trending in terms of quality or defects within the industry in 2026?
Well, we're trending in the wrong direction, I would say. We've gone through this report now for the last 6 years, I believe, amassing data really since 2011. And you can really see the trends from when the technology changes happen in the industry, and where you start to see an uptick in quality defects when this is happening. And then it settles down, and then the industry, as it does, moves on to the next technology, and then there's an uptick again of defects, or there's some kind of other, policy issue or geopolitical issue, although things that are going on right now that are causing the current uptick. So this year, in what we call pre-shipment inspection, so when we're doing testing on the production line for every batch that's produced for modules, and we tested over 160,000 modules in 25. And we had the highest defect rate we've ever seen, which was 3.36%. May not sound like much, but really when you're looking at other industries having a 3.36% defect rate is pretty high. And then the question is why? Why was this happening, this uptick? And there were a number of reasons. So, the previous uptick was the switch from PERC to TOPCon. and there were teething issues with TOPCon. Then it started to settle down. And then last year, I think there was just so much coming together in terms of all the policy and geopolitical issues happening, that there are new factories, sprouting up everywhere. All of a sudden there's 50 gigawatts of production in the United States. There's new factories across Africa and the Middle East. And clearly these are not, really ready to go factories with, not experienced personnel. And, we think that these are key reasons, plus the ongoing evergreen reason of cost pressure.
Mm. And in terms of, these geopolitical drivers or perhaps influences on the quality of PV modules, does that also include like tariffs in terms of the wider supply chain? Is that disruptive?
Yeah, certainly. So first of all, with modules and cells, all the tariffs, and I think everybody always puts it on Trump, but there was a lot of this going on already during the Biden administration with the IRA, trying to encourage domestic manufacturing. But certainly, those tariffs, they picked on first Thailand, Cambodia, Malaysia, and Vietnam. Those were the first ones. And so then what did the industry do? They said, hey, well, the Chinese manufacturers decided, well, what about Indonesia? And what about Laos? We call it whack-a-mole. And then it started moving further west. So certainly those tariff and the tariff uncertainty and all the changes ongoing, that influence then, where the modules and cells were being manufactured. And then, of course, in the United States as well, with the FEOC rules, so the foreign entities of concern that are still, is not 100% how that's what the details are going to be. But already, the Chinese manufacturers were preparing for this legislation whenever it comes, and changing ownership, and being careful about how many Chinese, workers they can have, and that all has eventually an impact on the modules and cells.
And does it also impact the bill of materials as well? So the components within the module?
Yeah, actually, I just saw. I'm trying to remember. There was a press release just yesterday. I think it was Jinko. Signed a big contract with Next Power for their steel frames.
Yeah.
And I'm more than certain that's just for the American market, to avoid any kind of tariffs on frames being imported from elsewhere. So certainly it affects everything within the bill of materials that can be exposed to these tariffs. And the biggest one is the shoe to drop now with this the FEOC is the polysilicon. So if that happens, where 90 to 95% of the solar industry's polysilicon comes from China, then what are we going to do? You can do all you want about module manufacturing capacity in the United States, but if you don't have the polysilicon, then you can't do anything. They're struggling now to get cells made locally. So yeah, it certainly affects the full supply chain of the bill of materials.
Well, let's dig into some of the report's findings.
Sure.
In terms of technical details. I think one of the biggest issues that we've heard about in the industry in recent times has been glass breakage.
Yeah.
Right? We moved to larger format modules.
Yeah.
Glass got thinner. But I think what is a little bit surprising is some of the breakage has been on the rear side glass.
I would say almost all.
Really? Okay.
Almost all happening on the
Okay. But now, why is that the case?
Well, basically, because of the size and the weight of the modules, they're put into stress. So it's like a bathtub, right? Like when it's sagging, it goes into stress in the rear side, in tension. And this is what the tempering process does, right? Tempering of glass of these windows in here. That's what it's for, right? They pre-tension the glass, and the problem is when they move to 2 millimeter glass, it's no longer fully tempered glass. So they could do that with 3.2 millimeter glass when it was just on the front side. When they switch to 2 millimeter, then all of a sudden everybody's seeing on their data sheet it says heat strengthened glass. And heat strengthened glass has a significant reduction in the bending strength of the glass, and also with the temperature resistivity, but that has been less of an issue. So that means it can be stressed a lot less than fully tempered. And the front glass stuff that you see is usually handling issues, right? Or, of course, in the US, a big topic is hail. And so in the US, you'll see modules being offered, hail-resistant modules. They're basically 3.2 millimeter front side glass with 2 millimeters on the back. So
formerly standard modules.
Well, the standard would have been with back sheets, right? This is now with, it's just taking the best of both worlds, really. And you've got this super heavy module, but it's hail resistant. So that's, that's what we do in the industry. We react to the problems once they show up. So we still see front side cracking due to handling or hail. But when you see these cracks, coming from the junction boxes or from the edge holes, mounting holes, it's almost always on the rear side. There's a number of other factors. It's never, this has been a growing part of our business, unfortunately, doing root cause analysis on glass breakage really throughout the world. So we just got an inquiry the other day about a project in Brazil that has these issues as well, but all across Europe and the US. And it can have a number of issues. Some of it are manufacturing related and the glass itself. So we already talked about the properties, but also the quality of the glass. So even if you have this, let's say, specific tensile strength it's supposed to have, it may not be homogeneous, for example. Okay. So you have, different levels of strength throughout the glass, in these large format modules. There could be, not clean cutting holes of the junction boxes, for example, or the mounting holes. And all of this leads to higher stress concentrations throughout the module, which makes it more fragile at the end of the day. And the other thing is the additional loads. So the larger they get, the larger overhang they have, the more exposure they have to wind loading, right? And so not just in trackers, this can also be fixed tilt. I think you see it more in tracker structures. But this, additional loading and asymmetrical loading as well is all happening to weaker glass, which is more fragile. And so then, somebody comes along mowing the grass, and a stone pops up and hits it, and it might be this little tiny thing, and all of a sudden, boom, you'll see the indent of the stone, and then it's a massive crack in the back. Now that's, I use that example on purpose because that's what a lot of the module manufacturers are saying now, right? It's pointing the finger at, it's your O&M, which may have been the actual last cause, but is the glass really fit for purpose? When it's so fragile that doing, a pretty standard thing in the industry, okay, and you can talk about, you should have covers on your lawn vegetation cutting equipment, reduce speeds of vehicles going through, et cetera. There are ways to do it. But if it is so fragile that, a little pebble or stone can actually, completely destroy the module at the end of the day, you have to ask yourself if the glass is really fit for purpose. And that's where we are right now.
Yeah, a module should be able to withstand a pebble.
Yeah, I would say so. I think some would beg to differ on the manufacturer's side, but yes, I would say so. Now, and that's the other thing. It may not also have been a pebble. I think that there's, you hear a lot of it in the industry that it's all the stones, but we do microscopic analysis then on the rear side and trying to find where that crack originated from. And often that's a starting point of a bending failure as well. So, there's a lot of literature on glass because, it's a standard building material. And so you can see what kind of glass patterns are out there, fracture patterns. So again, we're learning a lot as an industry where before it was, backsheet cracking when there were backsheets, and now we've got this glass issue. And I don't know what the percentage is these days, but just about every utility scale project, at least in Europe, will be a glass module with this size, heat strengthened, et cetera. They're all pretty much the same suppliers of glass. And so everybody's got this issue, and it's just a matter of, okay, did they do enough quality control in the factory, and ensuring that the right loads have been tested for, and all that. And if you're lucky enough, then you won't get glass breakage, and hopefully it will be rather limited, the effect, but they're much more fragile than they used to be.
Well, and another factor, as I understand it, is also the module frame, right? You mentioned the steel frames that Next Power and Jinko Solar are collaborating on, right? Thinner frames.
Thinner frames. We're down to 30 millimeters. I think when we started it was 45 millimeters. Now we're down to 30, and that's not the end of it. Then you look at the cross sections, all the walls of the frame cross section have all gotten thinner as well. And then not only that, this is another thing we've seen and highlighted in our report as well, are frame defects. So not just a dent in the frame, but also the sealant. If the sealant's not done properly, then you can have metal to glass direct contact, which is never good either. Another stress concentration, right? And all these things add up. So that's something we've been seeing where we've added, and this is how we adapt as Kiwa PI Berlin with our lab testing procedures as well. We've had to come up with new ways of, trying to understand, more about glass breakage. We do a cross section cut of the module frame, and then we can see, okay, what does the silicon look like? How well has the sealant actually been put in the frame? And you do see that there's actually glass to glass contact, or you see that the glass isn't centered properly, and so it's got a little bit of a twist to it, and that can mean that it's not all sitting in the frame at the exact right spot. So all these things, again, they all sum up to a more fragile and weaker module.
Now, I was interested in the report when you were presenting it, or some of the findings here at the Solar Quality Summit. You noted that actually cell alignment, or rather misalignment or spacing, was one of the failure types that you've been picking up. Now, it seems like a fairly basic thing, or it seems like something that the industry should know how to do better. How surprising was it for you?
I think this is like the frustrating thing for us that have been in the industry. I mean, you have as well, where you take two steps forward and one step back. We were at an event last year. If you go to any of the module specific events and you hear the manufacturer speaking, it's all about cell efficiency and trying to say, look at these, innovative technologies, and it is amazing, right? But you kind of think, have we lost the plot maybe? When really kind of basic things as part of the layup process, your setting of the cell strings in the module, and making sure that those distances, the clearance distances between the cell strings, or at the edge of the module, the creepage distance, it's been exactly the same in the standards, the IC standards forever. Something you would actually really kind of take for granted that it will be done, and now we're seeing, for some reason, more and more of these defects. Now, I'd have to do an additional analysis of the data. I assume that this is happening more in those, let's say, immature factories that we spoke about at the beginning, right? That they're, with all these new production facilities opening up, they need time to ramp up and to ensure that they do their processes correctly, and they're using new equipment. They've got new people that have to be trained, et cetera, and may also not be as fully automated as, let's say, some factories in China or in India, for example. And so that's likely where it's coming from. But yeah, it's fairly basic stuff and has significant consequences, right? So if the cell is too close to the frame, for example, you could get arcing in the field. We've seen that. There's another root cause analysis. We get called in. Hey, the module has burned on the edges around. Yeah, there was an arcing event. An arcing event, if it's on top of dry vegetation, you could be having a significant fire on the site, which is obviously never good. So it may seem like some kind of banal defect, but it can have significant consequences.
Yeah, very simple in one way, but also really quite serious in another.
Exactly.
Now, you mentioned kind of the technology shift that we've seen in terms of the cell,
the
transition from monoperc to TOPCon. that has also brought about with it some challenges in terms of degradation, right? Sensitivity to moisture being one, but also one that we're hearing more about is UVID. So that's
Yeah,
ultraviolet induced degradation.
correct. Yeah.
What's your understanding of where we're at in terms of our understanding of this degradation type?
Yeah, so I think what we have understood is, and again, this is a little bit of the combined issues that come to the fore. So TOPCon technology was a fairly well known type of technology. Even at the time of PERC, people knew about TOPCon and also back contact. But once it gets into mass production, then we start to see issues. And with the silicon oxide a passivation layer that if it should be able to handle UV properly, but as cost saving measures, that passivation layer was changed, was also made thinner, and then all of a sudden the UV sensitivity, which we all knew about but had protected properly before, was now exposed again. And so this is what has happened. It first started popping up in testing laboratories. And in testing laboratories, we follow a standard that has been a standard probably for the last 20 years. I don't think it's changed for UV testing. And it's very limited, right? When those standards were developed, they were just developed by Northern European countries, and so weren't thinking about a lot of high, UV dosages. And really, that exposure, that dosage is maybe 6 months in some places at the most, maybe a year. And so you could do double that. And, with the PVAL PQP scorecard, they do 120 and kilowatt hours per meter squared. And that represents maybe a year to 2 years, depending on the location of the site. And we are seeing significant levels. We're not just talking 1% to 2%, but I remember there was even some modules that they tested that went up to 16%. And then the question was, well, what's really going on here? Now, the question was, is this a laboratory issue, or is it actually something that's happening in the field? And that's really the most important thing. And I think that question hasn't fully been answered yet. There's some initial findings from Fraunhofer ISA that's been doing some testing. We did a little bit of testing, but we don't have great facilities in Berlin to have high amounts of UVID for long of UV for long enough. But a couple of other things were discovered, and another, let's say, buzzword for TOPCon is metastability, meaning that it's not stable once it comes out of the box. I think we all knew this from thin film technologies in the past. A little bit surprised that this was actually affecting TOPCon modules, meaning that once you take them out of the box, or dark storage is the term that's used, they actually have to be exposed to light for a certain amount of time so that they become stable. And then you should perform an initial flash test to see actually where the module is before you do the UV test. And this could be a couple of percent. So that can certainly affect maybe a pass-fail, because once these UV reports start to come out from people like us and others, the banks and investors were like, hey, wait a second, what does this mean? We're talking, sometimes here double digits of degradation, or at least even 6-7%. This is very significant if this is going to be real. So let's just say we're going to put a strict criteria here, and they worked with industry experts and decided, some of the banks really pushed on it to say, okay, at this level of UV dosage, you're only allowed 1.5% or 3% or whatever the cutoff may be. And that metastability then issue, if it hasn't been done properly, could be the meaning of if the modules pass or fail, right? And so we've seen that. And so that's something we've all learned as testing laboratories, that we need to ensure that the modules are stable before they get tested.
And also the module manufacturers as well,
Module manufacturers as well. This has been a topic of discussion as well. How should they be using TOPCon reference modules that aren't necessarily stable? Who knows where the calibration module is sitting for the whole day? So some have gone back to actually using PERC modules because we know that they're stable, and then calibrating accordingly their reference. So they are aware of it, but they're also a little bit, let's say, later, surprisingly in a way, but catching on to everything. They understand the issue, but have they actually addressed it in all the factories? And that's something that we're looking at too when we perform our audits.
Yeah, it's again that relationship or that dynamic that you mentioned right at the start, whereby new processes, new technology, new factories, there's always a time of developing the processes, of developing the deep understanding that you need to get it right, to make it accurate every time.
I mean, on our panel yesterday, there was a module manufacturer, and the representative was saying, like, they know, like, this is a, like you said, it's a very dynamic market. They have to keep pushing and pushing and pushing. They're under pressure, but also it's, what's really driven the industry, right, to where it is today in terms of, how cost effective solar energy is, and the efficiencies that they've achieved. And that's all been through, hey, let's just try. Let's try. And trying means, they said yesterday, like, their pilot lines are gigawatts.
Yeah.
Like
incredible.
A pilot line to test a new technology is over a gigawatt.
Yeah. I've got to say, I always feel a little bit sorry for the module maker representative when they're on a panel with two quality assurance engineers, right?
For sure, and I appreciate the fact that they're willing to do it.
Yeah.
And I think there's some great representatives here in Europe of the module manufacturers that are, and they do their testing, and they meet with us. They'll come to our office and we'll discuss certain topics, and they want to get some feedback. Okay, what are you guys seeing in the factory? What are you seeing in the lab? They want to learn, they want to improve, but then they have to go back to to their headquarters in China, where the cost pressure is enormous. So the question is if they can actually, implement the things that they've been, even their own R&D teams are saying, hey guys, we should be looking at this matter a little bit more closely. And if it's, an uptick in the cost of production, we'll be like, no, that's not going to happen. So.
Well, talking about manufacturing footprint, just to kind of round out our discussion, you were saying that these new factories in Africa, there's some, in North Africa, North America, of course, this big explosion of module manufacturing, and how that can lead to risks when it comes to quality in production. Well, there's also discussions, there are perennial discussions here in Europe about reshoring manufacturing to Europe. Could what are the risks in terms of quality if we were to really establish manufacturing at scale back in Europe?
Yeah, look, I don't think it's a must that it has to be poor quality. I think, on the one hand, you may not have the same kind of policy restrictions. I mean, depending on what kind of incentives. There's been obviously for years discussions with the EU about, what kind of incentives are going to be there as part of the Net Zero Industrial Act, right? Of trying to motivate investors to come to Europe to produce modules. But, I assume at this point in time, even though there are some benefits that you can have if you can say you don't have Chinese manufacturers being used in a tender, but there's nothing restricting, any of the major module manufacturers to coming to Europe and opening up a facility that's different in the US, right? So that would already be, there's excellent factories in Vietnam and in Malaysia, for example, that are from the Chinese manufacturers of very high quality. So there's no reason why that couldn't be the same case, that they would come with their equipment and train their people and
expertise.
Yeah, and their expertise. I think that's always maybe a little bit, let's say, ecocentric of Europeans, that they still think that they're leading the R&D of module technology. Is certainly no longer the case. It's actually in China, but there are good research institutes here, and I think there's a highly skilled labor force, and so as long as they're trained well, and if anybody was buying modules using people like us to do the quality assurance, there shouldn't be this kind of level of issues we're seeing in some of these new factories we're seeing in other regions of the world.
Yeah, well, it's a really complex series of factors, collection of factors and drivers. So thank you very much, Stephen Jurab, the Executive Director at Kiwa PI Berlin, for joining the Smartery podcast and helping to unpick some of these different influences: geopolitics, technology, cost pressure, and even pebbles. Which can pose a risk to solar quality here at the Solar Quality Summit in Barcelona. Module discoloration, backsheet cracking, PID, these are all quite familiar failure types in the solar photovoltaic industry when modules begin to degrade and power output drops. Here at the Solar Quality Summit in Barcelona, we're discussing polymers because many of these failure types are linked to the polymer material and some of the production processes. My guest today is Chiara Beretta. She's a researcher, Sustainable Polymer Solutions with the Polymer Competence Center Leoben, the PCCL. Thank you very much for joining the Smartery podcast.
Thank you for inviting me.
Now, Chiara, why polymers, right? I've said some of these failure types. Just why are polymers so crucial in terms of these failures, and why is understanding more about polymers so important?
Yes, polymers, they play a very important role in PV modules because even though they don't participate actively to power generation, they determine often when the PV modules are going to fail. So usually we see that when packaging is failing, so when polymers starts to degrade, then also a lot of different problems can arise, such as moisture ingress, that then will lead to corrosion or delamination of different layers. And those are just examples of things that can happen when the polymer no longer can fulfill their function.
And within the PV module then, within the bill of materials, the polymers are primarily in things like backsheets or ECA, is that right?
Yes, exactly. So the polymers, even if we don't see them or if we are not aware of them, they are in a lot of different components. Because if we think about conventional PV modules, now with different configuration, we can have the glass configuration, or we can have the glass backsheet, polymeric backsheet type of modules. But we can also have, for instance, flexible PV modules or lightweight PV modules where also the front sheet will be made out of polymers and not, for example, out of glass. But then we have also ECAs, electrically conductive adhesives. We can have also organic solar cells where we have polymers. So they can be in a lot of different places. Also the junction box will be made out of polymers, cables, connectors. There are a lot of different components that are polymers.
And they're so important because the modules naturally are out in the field or on the roof, so they're exposed to sun, to UV rays, moisture, humidity, and big temperature variations as well. So all of these things can influence how the polymer degrades over time.
Absolutely. And how the polymers will degrade does not only depend on the chemical structure of the polymer itself, but we have also additives and stabilizers that are included in the polymer formulation. So just by design or by chemical structure, there will be some polymers that are more stable than others, but all the stability can be a lot influenced by the additives and by the stabilizers. So when we think about polymers, we don't have to think only about one molecule, but we have to think about a complex system that works together towards good performances and towards good results.
Well, and, I mentioned the bill of materials, right? We tend to think that means just, this type of backsheet, this type of cell, this type of, other encapsulation material or cell interconnection. But you're saying in terms of the additives, there's actually another layer of sophistication. How much understanding is there about the importance of this layer?
Yeah, this is a great question because actually I believe that there is not so much understanding of all the different components that are in a polymer when they are included in a PV module. So what we try to do is also to make more awareness of the complex system that the polymer is. And also, for example, you were mentioning encapsulants, and when we were thinking about EVA is a very well-known material, but also here you can find a lot of different EVA formulations based on which kind of antioxidants are used or UV stabilizers are used. And now that we are facing new materials such as the so-called POEs and TPOs. Here the matter becomes even more complicated because those are classes of materials and they do not define one specific molecular composition. So being transparent on bill of materials, we believe that this is a very important step that the industry should follow to improve also reliability and to make also more clear how degradation modes can happen in the field.
Well, we've seen in the PV industry in the past when there is a kind of change in technology, right? From aluminium back surface field cells to mono-PERC, there was a bit of a learning curve. The industry discovered some new kind of causes for degradation and for problems. We've now had this big transition to TOPCon. I feel like things like POE has become more commonly used, or even the kind of encapsulation stack, if you could say that, has become more complex because of TOPCon has new sensitivities to things like moisture and also to UV. How accurate do you think that is?
It's definitely true. We have been now receiving reports of different degradation modes that that modules with TOPCon cells are experiencing, and I think here we will still see some maybe new degradation modes that are coming when more PV modules with TOPCon cells will be deployed. So it's possible that there will be still some learning and some module optimization that has to be done, and this also in terms of encapsulation or in terms of bill of materials. So I believe that also here there will be some iteration before the technology reaches a very high reliability level. But I think we are already at a good point. There is already a lot of research going on and a lot of things are being understood and optimized.
There might be some surprises in the field in the
I
future.
hope not too many, but this is a risk always. As you said, when you change a component and you change, in this case, a lot of components simultaneously, like encapsulants, cells, interconnections, a lot of things can be unexpected, let's put it that way. So it's important always to test as much as possible and to test not only the single component, but the whole bill of material, because how the materials will interact with each other, this will determine then the whole reliability and durability of the product.
And just to clarify, you mentioned POE, so that's polyolefin, right? And that became more common in the PV industry, I think, kind of over the last 5 to 8 years or something like that. What was the other acronym that you mentioned, the new material being used?
I mentioned the TPO, and those are like also usually polyolefin-based materials, but those are thermoplastic, which means that the cross-linking chemistry here is different, while conventionally, now in the PV community, the POEs are intended, those polyolefin-based material that chemically cross-link during lamination, whereas the TPO materials, those are also polyolefin-based, but they might not chemically cross-link during lamination. So this also has influence then on the processing conditions and how the modules are processed. But we also see the multi-layer encapsulants, like the so-called EPEs, where you have the combination of EVA and POEs, and this adds a whole additional layer of complexity again, because you have more interfaces, more polymers that can interact with each other, and this is again a question mark, how they interact also with the cells and the other components.
Yeah, a whole new layer of complexity. Now, at the PCCL, you've been developing some technology that will provide some more transparency into the BOM, the bill of materials, and even a process that you can do that in situ, right? So if a module's out in the field, it's been installed for some time, you can actually analyze what the bill of materials is. Can you tell me a bit about this project?
Yes, for sure. So we work with the near-infrared-based spectroscopy methods, and we use this characterization method to analyze the bill of material and the composition of the bill of material of PV modules in the field. There are a lot of different devices available with different measurement range or with different hardware configuration, but especially we have been using a lot an handheld device that therefore can be just carried to the field to make some non-destructive measurements and to get information on the bill of material. This is a measurement that lasts only a few seconds, and thanks to having a database of different PV materials, we can quickly identify the type of polymer that was used with a certain degree of uncertainty in the PV modules that are in the field. So this is for us a very valuable tool that can give us more insights on why some degradation mechanisms are happening, if they are material related or not. This is something that helps us also in improving reliability.
And you've actually been using that out in the field. Tell me a bit about this kind of actual use case.
Yes, so within the Supernova project, this is a European-funded project where we work together with a lot of different partners. We have been collaborating with a PV plant in Italy, and this PV plant was installed, the modules were installed in 2011, and then this PV plant underwent a revamping process then in 2025, and we went there to investigate the bill of materials of the modules and to understand whether some specific failure modes that we observed, such as, for example, backsheet cracks, could be related to some specific bill of materials. So we went there, we did near-infrared spectroscopy measurement non-destructively, and then we collected all the data and we analyzed them later on. And we could see that the modules that were installed there had at least 3 to 4 different bill of materials, and that only one specific bill of material had some severe backsheet cracking. So thanks to this measurement method, we could understand what was the reason of the failure, especially for the material failure.
So I imagine, the park owner or operator was looking at their project and there was degradation, there was power output losses.
Yeah.
But they weren't uniform across the project, right? Is that what you're saying? There were certain sections.
Yes, the PV system was underperforming, but it was not a homogeneous underperformance. And what we could see also visually is that some modules would look pretty much fine, whereas some other modules had some severe cracks and then corrosion of the interconnection. I meant backsheet cracks and then corrosion. So also how the visual appearance of the module was not homogeneous. And this was also due to the fact that the polymers degraded in different way because also different polymers were used. So this was a very nice case where we could see how the material strongly influenced also the performance of the modules.
Well, and the Supernova project itself, it's been running for a few years. We saw the session here at the Solar Quality Summit. It's aiming also at kind of automating these processes. So you were out with a near-infrared device in the field with the boots on at the project yourself. There's a potential for that to actually be automated.
Yes, absolutely. So the ultimate goal of the near-infrared spectroscopy-based inspection is to be automated within a robotic platform, so that then the near-infrared spectroscopy tool will be placed on a robot that will then move around the PV plant and then perform automatic inspection. Because here the goal is not only to analyze the bill of material, but also to develop degradation models that we can use then to predict the remaining lifetime of PV modules. So with doing then periodic inspection on the site, we can monitor the status of degradation of materials and then also help to predict the remaining lifetime, because we always try to correlate then the performance-related information to the material-related information.
And there's also, intelligence behind it as well, because you're processing a huge amount of data, particularly if it's automated, because it'll be out in the field, potentially, this little rover, taking measurements all the time. You need to process that data.
Yes, absolutely. And for this, we also use artificial intelligence. This is not the part where we are directly involved, but of course, there are colleagues in the project that are developing these algorithms that collect automatically the data to categorize them properly and to assign them also in a sort of digital twin systems where also bill of material information are related to the module performance information, and where then all this data can be brought together to understand better how the change of the performances are, to explain better the changes of performances that we see.
And maybe even predicting
Yes.
when things could potentially go wrong in the future.
Yes, and the goal is to predict what can go wrong in the future, also to then perform a predictive maintenance. So, for example, if we realize that a backsheet material could be prone to cracking or could be about to produce crack, then we can put in place some operations such as targeted repair solutions for backsheets. This is something what could be put in place when we realize that, for example, the material is degrading faster than expected, or this is just a practical example.
Well, it's an exciting area of research. Like, I think it's so cool that you can go to an existing project and then kind of reverse engineer or kind of investigate and discover what's actually behind the failure. Because often we just don't know, right, precisely what's in the bill of materials.
Yes. This it makes me feel a bit like we are small Sherlock Holmes going there with our small magnification lens and trying to figure out what's happening. Yes, this is an exciting part of the job also.
Well, thank you very much for joining the Smartery podcast. Chiara Beretta is a researcher of sustainable polymer solutions with the PCCL, and thank you for watching. This podcast is a Climate Copy production. Nicole Schäfer is our graphic designer, Ina Gossen, Wolfgang Weicht, and Peggy Herter-Zille are our marketing team. And Matthew Denny is on the edit. Be sure to follow, like, and subscribe on YouTube, Spotify, Apple Podcasts, or wherever you found us. And get in touch with comments, feedback, or suggestions at podcast@thesmartery.com. The Smartery takes place in Munich this year on the 22nd to the 25th of June, and I hope to see you there. I'm Jonathan Gifford, and thanks for listening to the Smartery podcast.